All right, so we've looked at friction a lot, but today we're actually going to talk about when we want it, when we don't want it, and also two types of friction, static and kinetic friction. So a lot of the times in society it feels like we don't want friction, right? When you're cooking an egg, you don't want it sticking to the pan, right? If you're skiing, you like wax your skis to try and reduce as much friction as possible so you can pick up speed. But sometimes we actually do want friction, right? When you're walking on the road, you don't want to slip. When you're driving your car, you don't want to slide, right? So there are some sections where we want it and some sections where we don't want it. Now usually friction will resist motion and always act in the opposite direction of motion. But there are two types of friction. One is called static friction. We haven't talked too much about this, but static friction is a force that prevents a stationary object from starting to move, right? For example, if you push hard against your hands and then try to slide them across each other, right, there's a force that prevents you to do so. That's static friction. But then once your hands start sliding, this is called kinetic friction. Okay? Kinetic friction comes from the word kinema, right? And kinema, right, the movie industry just changed the K to a C and called it cinema, right, which is moving pictures. Right? So the word kinema comes from motion. So kinetic friction means friction due to objects in motion. Now, it is a little bit tricky because it has to be the two surfaces that are in contact. Right? So for example, if you had a ball or a wheel of a car rolling, this is actually static friction. Because even though the ball is moving, if I were to mark like one little point on the ball, okay, that point does not rub against the surface like this. It only comes into contact at a single point. Okay? So if I were to show you an example and draw on this ball with a dry erase marker, and then roll it across the surface of the board, you see it only comes in contact and then it doesn't rub up against that surface. However, if I were to do that, that's different. Now it slides across. This is static, this is kinetic. Right? So a car that's driving on the road has static friction. Unless you hit the brakes and you're on ice, the wheels lock and your wheels start sliding against the surface. Right? When we talk about static and kinetic friction, whether it's stationary or in motion, we talk about those two surfaces that are in contact. If those two surfaces are stationary relative to each other, it's static. If they're moving across the surfaces of each other, it's kinetic. Okay, so moving on, there are lots of things that we'll do to actually help reduce friction, right? Like ball bearings, right? WD-40, right? If you're swimming, right? Or cars, which are streamlined, right? Streamlined means they're able to pass through a fluid like air more easily. So an example of a car that's not streamlined would be the Nissan Cube. And you wouldn't really drive that on a highway because you're just smashing into the wind, which is slowing you down, creating a lot of drag, and therefore using up a lot of fuel. But of course, perfectly fine to use it if you're only driving slowly in the city. Let's try a practice problem, see if we can figure out when we want friction and when we don't want friction. So here's some questions, some examples. We're going to say when friction is helpful or when it's not helpful. So turning a doorknob. So turning a doorknob a lot of people assume you don't want friction, so it's easier to turn, but without friction, you wouldn't have any grip. So it would be impossible to turn. So in this case, friction is helpful. Streamlining. So like I talked about before, right? Do you want a lot of friction if you're driving the Nissan Cube on a highway? No, you probably want something that's a little bit more streamlined. So in this case, we don't want friction. I'm just going to write no friction. We don't want friction. Pushing a heavy box across a rough surface. Well, if there's more friction, that's going to be a lot harder to push. So again, preferably no friction. However, even though I say no friction, you wouldn't technically want zero friction. Because if you didn't have any grip between your shoes and the floor, you're not going to be pushing that box very well. You're going to slide on the floor and fall down flat on your face. Right? So you do want a little friction. Tying a knot. In this case, you want friction. If you didn't have friction, you tie that knot, it's going to come completely undone. You want it to be able to hold in place. In this case, it's very helpful. And a car going around the curve, well, you can imagine a car going onto an on-ramp to a highway during the winter when there's ice. That's very dangerous. Why? Because there's less friction. You're going to slide off the road if you go too fast. So when you're going around a curve in a car, you want that friction. So it's very helpful. All right, so we're going to analyze some problems, like motion problems, like we did before. And like we did before, we're going to draw free body diagrams. Now we're going to start looking at situations that have frictional forces. Right? Some of the biggest problems that I see on tests when students analyze these problems is, one, they don't draw a free body diagram, which you need one. Right? Because remember, when you're analyzing Newton's second law, it's not the applied force equals ma or the frictional force equals ma. It's the net force that equals ma. So you're going to need to add all those forces. And if you don't draw a free body diagram, you might forget to add one. Or, another thing I see a lot of the times, is you might forget what direction they are. Right? You might have one east and one west. Right? And remember, if you have, say, 5 newtons east plus 5 newtons west, that does not equal 10 newtons. Right? You'll have to take, for example, west and make it negative east so that they will add to 0. And so it's important to include directions. Always write directions. Now, how do we actually calculate friction? Well, what does friction actually depend on? It depends on two things. One, what are those surfaces that are in contact? Is it rubber and concrete, rubber and asphalt, or rubber and wet asphalt, or rubber and ice? Right? Obviously, what those two surfaces are that are in contact will affect friction. And so we have this coefficient right here. This is called, it's a Greek symbol mu, and it is called the coefficient of friction. And it's a number that simply depends on what those two surfaces are. Right? And usually you'll have to calculate it by taking the ratio of that force of friction divided by the normal force, because the normal force is what will also affect the force of friction. Right? You can imagine trying to push a heavy fridge across the floor. Now there's a certain force of gravity down, therefore there's a certain contact force or normal force up. Right? In this case, there's a lot. So you might call your friend over to help you. But your friend decides to sit on top of the fridge. That makes things worse, doesn't it? He hasn't changed the two surfaces in contact, but what your friend did was increase the normal force and therefore increasing that force of friction, making it even harder for you to push. So to calculate force of friction, we simply multiply by this ratio, which is what those two surfaces would be. And in any question, I would either give it to you or ask you to solve it by finding that FF over Fn ratio and multiplied that by the normal force. Okay. Another thing is that coefficient is different depending on whether it's static or kinetic friction. And the coefficient of static friction will always be larger than the coefficient of kinetic friction. I'm sure you can visualize this, so go back to the example of pushing a fridge. Now, you probably have the idea that, or the feeling, because you've pushed something heavy before, that it's harder to get it to start moving than it is to keep it moving once it's started. And that's the idea that static is bigger than kinetic. Okay? It's harder to get it to start moving, but then once you have it moving, you don't want it to stop moving. Because once it stops moving, you have to get it started again. Okay? So this value will always be bigger than that value. So I've said a lot. Let's see if we can put this into practice and try some example problems. So here's the first question. It says determine the appropriate coefficient of friction in each case. Case 1. It takes 59 newtons of horizontal force to get a 22 kilogram leather suitcase just starting to move across the floor. All right, so what does this mean? Let's draw a free body diagram. Now you have some applied force, okay, and you're trying to just get it starting to move. So that means there's some frictional force, specifically static friction, because it's not moving and you need to apply a certain amount to just get it started. And of course we have our gravity and normal forces. All right, so the coefficient of friction, if we go back to the equation, right, which I have on your sheet here, right there, we can rearrange this equation to say that the coefficient is the force of friction divided by the normal force. Right? If you like, you can even put this into a triangle to help you rearrange, right, where you'll have frictional force here, coefficient here, and then normal here. So going back to the question, to solve it, we need to know what that frictional force is and what that normal force is. Well, to just get it to move, that means our applied force would need to equal that maximum value that static friction is. So they tell us that. That's 59 newtons. And then we need to figure out the normal force. Well, in this case, you have an object sitting on a horizontal surface. Right? There's no vertical acceleration. It's not taking off or going into the ground. Right? So gravity is equal to the normal force. So we can calculate the normal by just setting it equal to mg, which is 22 kilograms times 9.8. So mu would be FF, which is 59 newtons, divided by Fn, which is mg, or 22 kilograms, times by 9.8 newtons per kilogram. And when we do that, we get the value 0.27. Now the coefficient, if you look at the units, in our units here, kilograms cancel and newtons cancel. So there are no units for the coefficient. There's also no direction. is simply a ratio. Now, if it took 59 newtons to get that suitcase to start to move, here it says it takes 54 to keep it moving. So again, slightly less. Whereas in part A, we solved for the coefficient of static friction. In part B, I should write FS. In part B, we're going to solve for the coefficient of kinetic friction, which will be Fk over Fn. That's the exact same thing. Fn hasn't changed. But what has changed is Fk. It's no longer 59 newtons, it's 54 newtons. So we will write 54 newtons divided by the mass, 22 kilograms, times gravity, 9.8 newtons per kilogram. And we get a coefficient which will be slightly less, because it's kinetic, of 0.25. All right, let's try the next question. Here we have a worker of a moving company places a 252 kilogram trunk on a piece of carpeting and slides it across the floor. Ooh, carpet. At a constant velocity by exerting a horizontal force, so that's our applied force. What is the coefficient of kinetic friction? So let's draw a diagram. We have an applied force. There's some kinetic friction opposing it. And then, of course, we have, again, gravity and normal. Now, in this case, this is actually very, very important. It's moving with a constant velocity. That tells us that there's no acceleration. And if there's no acceleration, all the forces are balanced, meaning normal equals gravity, and applied force equals kinetic friction. So even though they directly say the applied force is 425 newtons, because they're saying it's moving at a constant velocity, we know that these forces must be balanced. So the kinetic friction must also be 425 newtons, just in the opposite direction. So when it says, what is the coefficient of kinetic friction? Well, we can do our ratio of F of kinetic friction over F normal. Normal will be equal in magnitude to gravity, and kinetic friction is 425 newtons. Where gravity is mass, 252 kilograms, times 9.8 newtons per kilogram. That's also very important, because on tests, I will see a lot of students simply write that gravity is 9.8. It's very important. 9.8 is the acceleration of gravity or the strength of the field. It is not the force of gravity. The force of gravity is how heavy something is, and that depends on the object's mass and the field. Right? So always do m times g, m times g, m times g. Okay, and when we do that, we get 0.17. Again, no units, no direction. The coefficient is just a ratio. Then it says, what happens to the coefficient if another 56 kilogram trunk is placed on top? This is like our friend sitting on top of the fridge. All right, so it sounds like if we place another trunk on top, that would somehow increase the value of the coefficient. But it's almost like a trick question, because it doesn't increase the value of the coefficient, it increases. If we increase the normal force, we're increasing the force of friction. And they both increase with the same proportion. in order to keep that ratio the same. So for part B, mu k will still be 0.17. It becomes harder to push because the normal force increases, therefore the force of kinetic friction increases. So it becomes harder to push. But the coefficient is only dependent on those two surfaces in contact. So unless you did anything to change those two surfaces in contact, then it stays all the same. All right, for our last question, we no longer have something moving at a constant velocity. In this case, a hockey puck slides along the ice at a certain speed. Then it hits a rough patch that's 5.1 meters across. Now the coefficient of kinetic friction for that puck and the rough ice is 0.47. So first, we'll draw a free body diagram. If it's moving in this direction, it means kinetic friction will be in the opposite direction of motion. Okay, but be careful, you do not always need an applied force if it's moving forward. In this case, the only horizontal force is kinetic friction. And remember, forces cause change in motion, not motion itself. Meaning, this is going to cause an acceleration. It's going to be a negative acceleration, so the hockey puck's going to slow down. And that makes sense. Okay? And of course, we also have our gravity and normal, which will be equal and opposite. Okay, so there's our free body diagram. Now it says calculate the kinetic friction acting on the puck. Okay, so if we were to apply Newton's second law, we get F net equals ma. Right? Now if we're just looking at our horizontal components, because remember you can treat everything horizontal completely separate from vertical, the only force you have is Fk. So F net is going to be our kinetic friction, which equals mass times acceleration. Now it says to calculate kinetic friction. Great. Kinetic friction equals mass times acceleration. Mass we know. Acceleration we don't. But what I do... Alright, so just to recap. Right, we do not need an applied force forward. Right, just because we're moving forward. In this case, we're slowing down. And forces cause change in motion, not motion. So kinetic friction will be in the opposite direction of our motion, causing it to slow down. And so we know that net force equals ma. And what we can do is we can calculate the kinetic friction a different way. All right, so the video keeps stopping, but kinetic friction, we know from the equation is mu Fn. Right? We know mu and Fn in this situation, right? Since we have no vertical acceleration, all our forces are balanced. Fn equals mg, which is just mass times 9.8. So that'll give us our kinetic friction of 0.78 newtons. Now I'm going to add a part C to this, where we would calculate the acceleration, right? Which we can use here. So if part C says find acceleration, okay, this is A, B, and C, we can use Newton's second law to find acceleration. We just divide both sides by mass, and you get acceleration to be the force, 0.78 newtons. And in this case, our friction is our net force, because that's the only force acting horizontally, divided by our mass, so 0.17 kilograms. And you see our acceleration will be 4.6 meters per second squared, because newtons per kilogram has identical units to meters per second squared. Right? And it's in the same direction as friction, which is, we'll just say backwards. And so there is acceleration. Okay?